So for this next topic, it's worth pointing out that molecules that we've been talking about don't exist in two dimensions. They actually have three-dimensionality associated with them. They take up volume in space. So we know that both of these are sp3 hybridized, and so we know that the overall three-dimensional geometry of this molecule is a tetrahedral geometry. And so we can actually describe this tetrahedral geometry on paper utilizing these wedges and dashes that we kind of introduced in the last video. So it turns out, just by including one wedge and one dash on each of the carbons right here and right here, we can very effectively describe the tetrahedral geometry of each carbon. And this would be the alternate way that you could draw it. So instead of having these two hydrogens that are kind of solid lines, meaning that these hydrogens are in the plane of the paper or the board, you have one going up and one going down in this case. You have both of them going up for this case. And what we're going to find out in the next couple minutes is that one of these descriptors is more right than the other. And the way that we're going to describe this, to try to explain which one is more right, is we're going to try to use a mental model called a Newman projection. And to really understand a Newman projection, what you have to do is you have to kind of imagine yourself being shrunk down to the size of this molecule. And once you've been shrunk down to the size of the molecule, you could then imagine yourself looking along this carbon-to-carbon bond. So this is a little eyeball that's been shrunk down to the size of a molecule, and it's now looking along that carbon-to-carbon bond. And if I was to look this way along the carbon-to-carbon bond, this is what I would see. I would actually see three different hydrogens that are kind of pointing left, right, and down. And we can actually give these left, right, and down hydrogens their own name, A, B, and C. It would seem that from this perspective, this A hydrogen would be pointing down, so that's this hydrogen right here. This hydrogen is pointing to the right from this perspective, so this is hydrogen B. And this hydrogen is pointing to the left, that's hydrogen C. So now we can see what hydrogen is what from this perspective. And we can also now draw in these other three hydrogens. So if this hydrogen A is pointing down from this perspective, that must mean that this hydrogen is pointing up from that same perspective. And then we have one hydrogen right here pointing left and one hydrogen pointing right. So to complete the Newman projection, this is what it would look like. So we're going to get to the rationale as to why one of these structures is more correct than the other in a moment, but for now I need to give a little bit of a couple of definitions. So this hydrogen B and this hydrogen right here, they have a relationship that's so common they get their own name. So this relationship between hydrogen B and this hydrogen down low is called a gauche orientation. And the relationship to this between this hydrogen A and this hydrogen up above is called an anti-orientation. And we can describe these two orientations by the degrees of separation between the two atoms. So between hydrogen B and this hydrogen, we actually have a 60-degree angle between the two, if you completed this line right here. And between these two hydrogens, hydrogen A and the hydrogen up above, we have a 180-degree orientation between these two. So a 60-degree orientation is a gauche orientation, and an anti is 180. Now if I looked at this conformation of this ethane using a Newman projection, if I took my little eyeball, I looked along this carbon-to-carbon bond, I'm going to get a different Newman projection, where this is HA, HB, and HC. And so from this perspective, HA is pointing up, and so that must mean that this hydrogen is also pointing up. And so in reality, this hydrogen right here in the back would be completely covered up by HA, but just for the sake of drawing this where we can actually describe the difference between the two, I'm going to try to draw this hydrogen as close to this hydrogen as possible. So other than having this gauche orientation and this anti-orientation, this type of orientation also has its own name, and this orientation is called an eclipsed orientation. And the angle between these two is going to be 0 degrees. So 0 degrees, even though it looks like it's more like 15, this is just drawn so we can see it. And so now we have to remember that this carbon-to-carbon bond isn't static. It doesn't just kind of sit like this. This sp3 hybridized carbon can actually have this single bond rotate in three-dimensional space. So what's really happening is you can imagine this kind of like a pinwheel where HC, HB, and HA are kind of moving in a circular fashion. Okay, so we can actually rotate this bond right here. And you could imagine that if you rotated this bond, you would eventually get something that looks a little bit like this, where HA is pointing upward, and HC is pointing to the right, and HB is pointing to the left. And so an analogy here is that if you envision these hydrogen atoms or any other group as taking up three-dimensional space, they're kind of like a wrecking ball. And so if they get really close together, you can imagine two wrecking balls kind of clashing up against each other, and that's going to be a very energetic, unstable situation. So if we rotate it along the carbon-to-carbon bond, we can actually draw out an energy diagram, where on the y-axis you have energy, and on the x-axis you have rotation. And if you took this Newman projection on the left and you graphed it on the energy diagram, it's going to turn out that this is going to be much lower in energy than the Newman projection on the right. What you would see is if you rotated this front part, you would end up going from a very low energy to very high energy. And you'd get this kind of oscillating wave where if this is A right here, then A would be down here on this energy diagram. And if this was B, B would be right over here at a local maximum.